Hey, welcome back. Welcome back. This is now 9.9. We're actually going to get our hands on the representation of functions via power series. So let's dive right in. So the method we're going to introduce here is not kind of the ultimate method. We won't get that method until 9.10. The way we'll do it here, though, is very similar to what we did back in section. And it's related to one of the quizzes, 9.2. If you remember that video quiz you took in 9.2, it's related to that. Okay, so that turns out to be kind of a clever way of getting your hands on power series representations for functions. So what do? We use the geometric series. And for cases like we saw actually in 9.2, it was a bit idiotic to use the geometric series in terms of, in place of the given function. But now that we have this ability to integrate and differentiate power series, we can integrate the results of what you get from the geometric series in order to get your hands on something that is useful. Okay, so let's remind ourselves what we're doing. The geometric series is this guy. We are basically just going to replace r with x and then talk about that thing. Okay, we'll also want to get the radius of convergence. The way you get your radius here, though, is different than what we did with the power series and the intervals of convergence and that kind of stuff. We're not going to have to do that. If you go back to the way we defined the convergence of the geometric series, it's independent of kind of the process that you do for look, you don't have to do it, okay? You're not going to have to check endpoints is what it comes down to. The original proof for the geometric series takes care of that issue. It'll be divergent at the endpoints. So you need not have to worry about that using the ratio test. No, okay, that won't come into play here. So let me just write that down so there's no question as to what's going on. You don't need the check endpoints for convergence. Okay. The way we got convergence or divergence was sort of independent of the ratio test. We didn't have the ratio test back then. Okay. All right. So anyways, let's look at what's going on. So I want a power series representation for h of x equals 1 over 1 minus 2x. I don't know why, but let's just play along, right? How do I pull this off? Well, I can kind of identify the bits and pieces as A's and R's, right? So in this case, the A value is apparently 1, and the R value is 2x. So as a summation, at least, you can rewrite it as the sum of A, which is 1, so I'm not going to write 1, and then R, which is 2x raised to the nth power from n equals 0 to infinity. And then this thing will converge if the absolute value of 2x is less than 1, and then we can expand that to get the interval of convergence. So 2x less than 1 greater than negative 1 divided by 2. It's going to go from negative 1/2 to 1/2 for your IOC. Okay? Okay. Let's look at another one. It's problem 4. F of x equals 9 all over 4 minus x squared, and the center is 0. We'll shift the center. It seems like the first problems, the centers, these are harder. They're kind of out of order. Number 1, you have a shifted center, but right now the center is just 0. If you have a shifted center, basically what you're going to do is replace this R thing with an R minus C type deal. But anyways, to pull this off, we need a 1 in this position here. Okay, so I'm going to have to do a bit of fancy footwork with my algebra. So this would be 9 all over, factor out the 4. And so I can have 9/4 as my A value, and then 1 minus, you go x over 2 squared, or, you know, however you want to play it. I guess it won't really matter. So anyways, the A value is 9/4. The R value is x squared over 4. And now we can write our summation as 9/4 times x squared over 4 to the nth power from n equals 0 to infinity. You can simplify that if you want. There's not really much to simplify, but you leave it that way if you want. And then that will converge when x squared, the absolute value of x squared over 4 is less than 1. In other words, when x squared over 4 is less than 1 but greater than -1. And again, we can kind of solve for that. But you know, just thinking of the original inequality, that's going to be true where it's kind of weird. Is an absolute value on top of this? Well, anyways, visually, what they're asking for, the x squared over 4 function looks like this. And we want to know when it's greater than -1. So it seems like it's always greater than -1. But it was an absolute value function. Well, the absolute value of x squared over 4 is still just x squared over 4. All right? So it's always going to be greater than -1. The question is whether this thing is going to be. Okay, so anyways, here's -1, here's +1. So the only time it's in between those two dashed lines is when it's in this interval from here to here. So you just need to figure out when is x squared over 4 actually equal to +1, these intersection points, right? So I mean, when x squared is equal to 4 and when x is equal to plus or minus 2 are those two values. So the interval of convergence, IOC, again, you don't have to check the endpoints. It's going to go from -2 to 2. All right. Let's look at a shifted version. So now, you know, we can handle problem 1 in the homework if we do this. So they want the power series representation for 1 over 7 minus x centered at 1. And this is craziness, right? I just make a side note here. I would 99% of the time want to work with this function as opposed to this series, right? There's not going to be a day when you decide, whoa, this is a good idea to do this huge power series. No, and that's, you know, part of it is just saying, hey, we can make this relationship between this function and this power series, but the other part is going to be here a little later where we can actually integrate the thing and get a function of value. Okay, get a power series representation for something that we couldn't have done originally. But anyways, let's look at this guy. So what I need to do is kind of rewrite the x as x minus 1. So minus x minus 1. If I do that, what have I done? I've actually added in a 1. So I need to automatically get rid of it. I'll have 1 all over 6 minus x minus 1. Then I need a 1 in this position. So, you know, the goal for all of these is to get your expression in this form. And then when it's in that form, you can convert it to your power series over to here. Okay? All right. So I need a 1 in that position. So I'm going to factor out the 6 from the denominator and pull it into the numerator for the a value. So get 1 minus x minus 1 all over 6. And then that's pretty much it, right? So my a value is 1/6. The r value is this crazy x minus 1 over 6. So I have the sum of 1/6 times x minus 1 all over 6 to the nth power from n equals 0 to infinity. Now I need the radius, the interval of convergence. So that's going to be when this thing is less than 1. You can expand that thing. So less than 6, greater than -6, add 1 to all three sides, and that'll be our interval. All right, one more. So we can rewrite expressions like this by doing a partial fractions and then apply this idea to the individual terms. I think they're nice enough to do the partial fractions for you in the exercise at hand. Well, no, like number 4, they don't really do it for you. Number 5, they do. Well, number 4, we didn't even bother anyways, right? I guess we could have done a partial fractions, but we didn't. And I did number 4 in the notes up here. So there's multiple ways to pull some of these off. Anyways, number 5 gives you kind of an alternate approach. What you do is a partial fractions and decompose this thing, and then each one of those terms is basically very easy to convert into summations, into geometric series types. So in the first type, the R value would be -1, right? So you could rewrite 1 over 1 plus x as 1 all over 1 minus -x, and then plus 1 over 1 minus x. So the first R value is 1, its A value is 1, sorry, R value is -1, so it'd be -1, oh, sorry, -x. Butchering that. I'm wishing this problem didn't even exist, to be honest. So -x to the n from n equals 0 to infinity, and then plus this other series, and of course that's just x to the n. The R value is x, the A value is 1 from n equals 0 to infinity. We have the same indices, so they both start at n equals 0, so you can actually combine these two series. And on top of that, you can only do this where the individual series are convergent, right? So both of them are going to be convergent on that interval from -1 to 1. So the first guy is the absolute value of -x needs to be less than 1, but that's the same thing as the absolute value of x needs to be less than 1, which is x less than 1 greater than -1. And the second guy, the absolute value of x needs to be less than 1, but that's just x greater than -1 less than 1. So both are exactly the same intervals, and we don't need to worry too much about the convergence issue. But I'm going to go ahead and combine the formulas into one formula like this, and that should do it. If you want to get make it look a little prettier, you can maybe factor out the x to the n portion, and you'll have -1 to the n plus 1. Just depending on what index they're giving you. So they want it to start at 0. So that should do the trick. You could probably just put it in as I originally wrote it, but let me try x to the n times -1 to the n. Pad is not helping. Out of the way. Plus 1. And then the interval of convergence. Both intervals are -1 to 1. So you have to take the intersection of the intervals if they are different. It doesn't really come up in the homework though, so don't worry about it. Yay. All right. Okay, great. So let's then look at number 6. So number 6, they're starting to hint at this issue. You could produce new power series from these power series that you're generating via the geometric series by differentiating or integrating. Okay. So for example, number 6, and here you're going to have to check endpoints. So if you do integrate or differentiate, and in particular if you integrate, you must check the endpoints for convergence or divergence. Okay. Anyways, let's look at number 6. And we have the power series, f of x equals 18 all over x plus 1 cubed. Okay, so they are kind enough to tell you that, hey, this is just the second derivative of 9 over x plus 1. And that's nice because we know how to take the derivative of power series now. And in particular, that power series that we're going to be dealing with is just going to be a geometric, right? So we just need to take the second derivative of this geometric series, rewriting this a little bit. It's 9 all over 1 minus negative x. So the r value is negative x, and the a value is 9. So what do we got? 9 times negative x to the n from n equals 0 to infinity. And this is the stuff where now I start getting kind of careful about the terms of the series, because I mean I could just go ahead and differentiate once by differentiating the terms of the series, right? The only thing it's differentiated with respect to x. So this would be, and I want to be even more careful by rewriting this as 9 times negative 1 to the n times x to the n. Otherwise, I have to do a chain rule. And then I'm going to expand it to make sure that I get the right answer. So taking the derivative of that second series there, I'll have 9 times negative 1 to the n times nx to the n minus 1, right? So expanding that thing, plugging in 0, I would just have 9. And then the next term would be minus, so this is n equals 0. N equals 1, I get minus 9x to the first. And then when n is 2, I get positive 9x squared minus blah, blah, blah. And I need this new series that I'm creating to have the derivative of those terms. Okay? So I need the derivative of this thing. Or I'm eventually going to have to take another derivative there. But the terms need to be, well, what is the derivative of 9, right? So the derivative of the first term is 0. The derivative of negative 9x is negative 9. So my first term better be negative 9, right? So I think I'm going to let n equal 1 and then go to infinity and see if that works. So negative 1 to the 1 is negative, and then we have a 9, and 1x to the 0 is just negative 9. So that's the way to go. The next term should be 18x. So let's just make sure. So this is n equals 1. When n is 2, I'll have positive negative 1 to the 2 is positive 1. And then you have 9 times 2x to the first. So yeah, that works. Okay. And then I got to take the derivative of that expression again. So I'll have 9 times negative 1 to the n times n minus 1 times x to the n minus 2. And that better equal, well, let's see. All right. So this term right here was 18x. And if I take its derivative, that will give me the first term in the next series, which should be 18. The term after that would have been minus 27x squared, right? Because this term up here would have been minus 9x cubed. So yeah, 27x squared. Its derivative would be just minus 54x. Okay. It's taking the derivative. Okay, so I need that to equal that stuff, all right? So I have then, I guess I could just start at, if I start at 1, the first term would be 0, so I don't want that. So I'm going to start at 2. And so my first term, I want it to be 18, right? So let's see if it works. So negative 1 squared is positive 1, and then I have times 2 times 2 minus 1 is 1, and then x to the 0, which is 1. So yeah, I got 18. Then minus, let's make sure I get the next one. Minus 9 times 3 times 2x to the first. So yeah, it's working. So I get the 54. Okay, great. So, I'm going to go take this in. No, sorry, buddy. They want your series to start at 0. Okay, so I need to move this guy. So I'm going to move the 2 over and do kind of a substitution on n minus 2. So n will be j plus 2. So the series will be j equals 0 to infinity of 9 times negative 1 to the, now n minus 2 is going to be, or it'll be j plus 2, but that will be the same as just j. Okay. So y, well, if you have n versus j plus 2, right? So starting at 2, n is even, but if you add 2 to an even number, you just get an even number back. So n, whether you have n or n plus 2, it's the same. So instead of putting j plus 2, I could just put j there, and it'll still work. If you don't believe me, you could do it the other way. I don't think the answer in the calculator will matter when you put it into WebAssign. Anyways, then you have, instead of n, you have j plus 2, and then n minus 1 will be j plus 2 minus 1, which will be j plus 1. And then x to the j plus 2 minus 2 will just be j. And then when you put it into your answer here, you're going to put n's instead of j's. So I'm going to write 9 times negative 1 to the j, or in this case n. And if you wanted to, put n plus 2. I don't think it's going to matter. I'll put n plus 2. Okay. And then I have n plus 2. And then I have n plus 1. And then CalcPad is giving me the middle finger. And then I have x to the n. Okay, let's make sure that's right. Then we'll get the interval. Yay. All right, so I expect the interval, it's not going to gain any convergence. It'll probably be the same as what it originally is. And so for the original guy, we need the absolute value of negative x to be less than 1. So I'm saying x needs to be in between 1 and negative 1. And I'm not even going to bother checking. Okay. You can check each individual endpoint, but I'm 99% sure it's not going to gain anything, right? So in number 7, though, that's a different story. That may gain convergence there. So let's look at number 7. So again, they're nice enough to kind of give you a heads up. They're noting, and this one's important because now we actually get a power series representation of a function that we could use, right? Before, the power series representation is not very useful. Again, it's a matter of ease of accessibility. This thing is way easier to work with than this thing over here. Okay? But you may find that this new series that we create is easier to work with, and especially considering the fact that to work with a power series, in real life, we'll probably just use the first maybe 10 terms of the power series. So it's basically you're working, instead of with a natural log function, you're going to work with a polynomial. And we all love polynomials. They're so easy to take derivatives of, etc. Okay, so anyways, let's take a look at this guy. 1 over x plus 1 is the same as 1 over 1 plus x. And of course, we could rewrite that as 1 over 1 minus negative x. And so our r is negative x, and our a is 1. So this will be the sum of negative x to the n. And I'm going to rewrite that by factoring out the negative portion. So this will be the sum of negative 1 to the n times x to the n. And that equals 0 to infinity. And then to get my hands on this natural log function, I'm going to be taking the integral of that series. And again, I'm going to be worried about the index if I need to shift it over or whatever. Right. So anyways, just blindly listing out the terms of this. Maybe we can just, no, I don't think we're going to be able to do that. But what is this thing, right? Okay, sure. Let's list out the terms. So n equals 0, I get 1. N equals 1, I'm going to get negative x plus x squared minus x cubed plus blah, 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 dx. For the integral, then, you could integrate just the expression. So in this case, you would need to integrate the x to the n part. So that would give you x to the n plus 1 all over n plus 1. N equals 0 to infinity. But you can also integrate that polynomial thing there. So the integral of 1 is x. The integral of x is x squared over 2 plus x cubed over 3. And then make sure your summation notation syncs up with that. So it should be just what we wrote out there. So when n is 0, it should be just x, right? So you'd have x to the 1 over 1, so that works. When n is 1, it should be negative x squared over 2, and it certainly is. Okay, great. That's our series right there, folks. So we could plug that in. Its index is lined up the way we want it. And then we have x to the n over n plus 1. Okay. Row. What did I do wrong? Oh, it's n plus 1. And so n plus 1. Okay. All right, now I need the interval. And it gets a little tricky here, right? So the original series will converge when the r value is less than 1. So the absolute value of negative x is just going to be absolute value x. And that will be in between 1 and negative 1. But when you integrate, you typically pick up some convergence. So we need to go through and then check the endpoints. So check x equals 1. All right, let's start on the left. Let's kind of do it in order. So negative 1, we have the series negative 1 to the n times negative 1 to the n plus 1 all over n plus 1. Okay. What the heck is that thing? So that's the series negative 1 to the 2n plus 1 all over n plus 1. Negative 1 to the 2n plus 1. So let's do this out. Plus 1 and negative 1 to the 2n times negative 1. This is negative 1 squared to the n times negative 1. This is 1 to the n times negative 1. 1 to any power is just 1. So that will be negative 1. So the series negative 1 over n plus 1. Believe it or not, that's just a harmonic series, a multiple of a harmonic series. So if you were to write it out, you would get negative 1 minus 1/2 minus 1/3 minus blah, blah, blah. Which is a series n equals 1 to infinity of negative 1 all over n. So it's harmonic, it's divergent, no change there. So let's look at the other endpoint when x is 1. That will be alternating. Right? So negative 1 to the n, 1 to the n plus 1, 1 to any power is just 1, so that would just be 1. And we got to do the AST, tell your reader which test you're doing. So step 1, take the limit of the a sub n portion here, 1 over n plus 1. Limit of that is 0. Secondly, look at the ratio of consecutive terms. A sub n plus 1 is 1 over n plus 1 plus 1, which is 1 over n plus 2. A sub n is just 1 over n plus 1. Take the reciprocal. That's definitely less than 1, therefore it's convergent. Okay. So just as kind of, I think the pattern is going that we're gaining one endpoint convergence when you integrate. So negative 1 to 1, bracket. Okay, yay. Let's look at numero. I think it's 9 I want to look at. Yeah, 9. So this one a little bit harder, right? Because they don't give you what this thing equals. And number 7, they kind of tell you, well, this is a result of integrating 1 over x plus 1. So here you got to get creative and kind of figure out how am I going to get something such that when all is said and done, I get this ln of x to the 6 plus 1 out of it. And you know it has to be kind of the result of some sort of geometric, but let's take a look, right? So f of x is the ln of x to the 6 plus 1. Let's take the derivative, right? Let's just say what the derivative is. So f prime of x is going to be 1 all over x to the 6 plus 1 times the derivative of x to the 6 plus 1 is 6x to the 5th. And I believe we could work with that. Let's rewrite it a little bit. So the rewriting it even more, right? So you get 1 minus negative x to the 6. And then your a value you could put as 6x to the 5th, believe it or not, and your r value, try negative x to the 6th, right? So this will be the sum n equals 0 to infinity of 6x to the 5th times negative x to the 6th to the n. Let's get that negative 1 out of there by splitting up the negative x to the 6th to the n into negative 1 to the n times x to the 6th to the n. So I get 6x to the 5th times negative 1 to the n times x to the 6th to the n, which would be x to the 6n. Then you could add the exponents on like bases. So I'll have 6 times negative 1 to the n times x to the 6n plus 5 from n equals 0 to infinity. So that's the derivative of f of x. So in order to get back to f of x, I need to then integrate f prime of x, right? So I need to integrate this thing. If you're worrying about that plus c constant, it never is an issue with these types of problems, because if you think about what is the ln of, what is f of 0, okay? F of 0 will be the ln of 0 plus 1, which is the ln of 1, which is just plain old 0, okay? So you kind of know what that would equal at one of the points. So if you did, in fact, have this thing right here as your f of x, you would know that plugging 0 in there would give you 0. So what? Well, all right, so I have f of x equaling x minus x squared over 2 plus x cubed over 3 minus dot, dot, dot. If you plug in 0, and we're presuming that there's still a plus c involved in the picture. Okay. So after I integrated in this step, what I got was this thing, but with a plus c, right? And what I'm saying is when you plug in 0, we know the answer has to be 0. Okay, but if I also plug in 0 into the variable x, I'll have 0 minus 0 squared over 2, which is 0, plus 0 cubed over 2, which is 0, plus dot, 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 and then plus c. And of course, that will just give you the equation 0 equals 0, because all of this junk is 0, and then plus c. So therefore, c equals 0, and it goes away. Okay, so that's why you don't see it in the work. It's why you're not going to see it here either. So anyways, what is the thing that we're actually integrating? If you want to look at the terms, starting at 0, you get 6x to the 5th. At 1, you get minus 6x to the 11th plus 6x to the 17th minus blah, 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 dx. So this will be the sum of 6 times negative 1 to the n times x to the 6n plus 5 plus 1, which is 6n plus 6, all over 6n plus 6. And let's see if we got our index starting at 0 still. So if I did integrate this thing, it would be 6x to the 6 all over 6. The next guy would be 6x to the 12th all over 12. The next guy would be 6x to the 18 all over 18. Is that what we got? Okay, so expanding this looks like you're going to have to start at 0. Okay, and you'll get 6 times 1 times x to the 6 all over 6. So yeah, it looks like it's working. Let's try one more. N is 1. You get 6 negative x to the 12th. Yeah, which is what we want, all over 12. All right, so we nailed it. That is then going to be your first answer, right? Okay, then for the quiz, I want you to figure out the interval of convergence, right? I will figure out the sort of the radius, but then you got to check the endpoints. So for the radius, you have to go back to the original R value, which is sitting right there, and say we have to have this being less than 1 for it to pan out, right? That's equivalent to saying that x needs to be in between 1 and -1. And it's basically, this is the same as saying you need x to the 6 to be less than 1. X to the 6 is always positive. So if you drew it out, you're probably going to get some sort of flattened kind of parabola looking deal. And then you want to know, again, where it's kind of hitting these points, because that will be where the function is actually less than 1 but greater than -1. So it's these 2 points that you're after, and those turn out to be -1 and 1. Okay, so you need to then check for the quiz, check what happens when x is equal to -1, and then what happens when x is equal to 1. So you need to show me the series, you need to simplify the series, and then do any tests that you encounter as the result of those expressions. So let me pause the video. Just some hints, some general hints as you're going through. Which dude are you working with? You're plugging those x values into this dude right here, okay? When on the first endpoint, when you're doing x equals -1, you're going to get a weird -1 to the 7n. You're going to get something that looks like this, 7n plus, if you do it right, 7n plus 6. And what is that? That's just -1 to the 7n times -1 to the 6. -1 to the 6 is +1. So you just get -1 to the 7 raised to the nth. And that will just be -1. -1 to the 7th is -1 raised to the n. So just kind of, hopefully that helps you in your journey. It will turn out that you have to do the alternating series test on both. Both series, once you do your substitution, should be the same. And then you should be able to get your interval of convergence from that. Okay, so let's leave it at that. As usual, thank you for watching, and I'll see you next time.